welcome everybody. So today we're going to talk about collision model and the collision theory, the idea that particles need to collide in order to react. And there's, a few different factors that affect the rate of a reaction. These things include how hot the reaction is, so temperature. It also includes things like concentration, surface area, if there's a catalyst, pressure if you're a gas, and also the nature of the reactants, what the reactants are made up of. And the nature of the reactants, that becomes really important because when we talk about bond strength and how easy it is to break the bonds, then the nature of the reactants, that's where that factor really comes in. So when we think about particles colliding, they need to collide in the correct orientation. And this mainly means that they have to be in the proper position in order to react. If they're not in the correct orientation, then they will collide ineffectively. We want the collision to be effective, meaning that it has the proper orientation. This could be if you have like a enzyme reaction or some sort of protein substrate reaction. You need the proper orientation for that induced fit. If you're taking biology, that should sound familiar to you. It could be that two particles, they need to collide properly so that a new bond can form between them. The other thing is the energy. And this really comes through with temperature effects. And what we see when we increase the temperature is that we're going to increase the energy of the collision. And so this is the other thing that makes the collision effective, is the amount of energy the particle has. And I had mentioned previously that when you double the temperature by 10 degrees, or when you increase the temperature by 10 degrees Celsius, then the rate will double for every 10 degree increase. And so that becomes really important when we think about temperature. When we increase the temperature, we're really doing two things. We are increasing the number of collisions, which is called the frequency of collisions. But then we're also increasing the energy of the collisions. So these two factors, the increase in the number of collisions and the energy of those increased collisions, really makes for a big increase in the reaction rate given the temperature increase. Okay, something else about collisions that I want to tell you about is only temperature does this with the energy. With concentration, surface area, pressure, these all affect just the number of collisions. And so since you're adding more particles effectively by doing concentration, surface area, or pressure, you are just adding the chances of there having a collision, effective or ineffective. And let's say that you have 10% effective collision rate here. If you have 10 particles, that means that 1 out of those 10 are going to be effective at colliding. But if you have 100 particles, now you have 10 that can be effective because it's still the same percentage. When we deal with temperature, it increases the effectiveness of the same amount of particles by increasing their energy. Okay, so let's talk about these potential energy diagrams. They don't do much with these per se in AP. They expect you to have an idea of what it looks like. This would be an exothermic reaction. But as a review, there are really 6 arrows that you need to know for this. And they show you 2 of the arrows here, if I zoom in on here. But there's also this arrow here, which I'll label 1. There's also, this arrow here that I'll label 2. There's this arrow here that I will label 3, and then there's an arrow that would go all the way to the top, to the bottom, and this would be arrow 4. This we can name arrow 5, the activation energy, and 6 is the heat of reaction, the delta H, which they have as delta E there. And so what this is showing you is that if we zoom out now, 1 is pointing to the potential energy of the reactants. And so these reactants have a certain amount of energy associated with them based on their bonds. If we heat these up, if we somehow or other get them to, like increase the potential energy, we can see that this bond right here starts to twist and starts to, like vibrate in a way that will allow it to break. And we reach a point here where we get to the top and they have this activated complex. That's what 4 represents, the potential energy of the activated complex. And so that is where the bond has broken and we are ready to form a new bond. And then we can see that at the product side we had this interconversion. And so when I look at arrow number 2, 2 is the potential energy of the products. Now, arrows 5 and arrows 3, those represent the activation energies. 5 is the activation energy of the forward reaction, whereas 3 is the activation energy of the reverse reaction if it occurred. The thing is activation energy, when I define it, you can see it at the top here, it's the energy required to initiate the reaction, and that's what we're talking about here. We start off as a reactant, we then put energy into the reaction, it causes this breaking of this bond. That's the activation energy to get that reaction going. Very quickly, the reaction will form the products, and you will get the product on the right side of the diagram. For IB, I would say know all 6 arrows. If you don't know them already, know all 6 arrows. This is exothermic. If I were to draw you, an endothermic reaction, it would start at a lower potential energy and end higher like this. This would be endo. Alright, let's talk about a diagram that you may not have seen. And this is showing you the energy of some reactants at 2 different temperatures. We have a lower temperature in blue, and we have a higher temperature in red. And what's added to this graph, you might remember this graph when we talked about gases. This is this Boltzmann plot where we have the average kinetic energy. Most of the particles at the lower temperature are here. This is where the majority of the particles are, down over here. At the higher temperature, the majority of the particles are over here. Look, in both cases, the particles, the majority of them, don't have enough energy to react. What they've done on this graph that's different is they've set a dotted line here that represents the activation energy, the minimum energy to cause a reaction to occur. Now what we see though is that even though at low temperature or high temperature most of the particles would fail to react, there are some of the particles, in both cases, high and low temperature, that are above the activation energy. But what we notice about the higher temperature is the fraction is greater. And this is what causes the reaction to be faster at higher temperatures. More of the particles can overcome the minimum energy needed to react. This allows the reaction to occur faster. It doesn't change the activation energy. The activation energy is set regardless of the temperature, but it allows more of the particles to rise to the occasion, to make it over that minimum, that bar. And this is what's happening when we have an increase in temperature. Now, there is a mathematical way to find the activation energy or the rate constant, and it is called the Iranian Equation. This is actually no longer on the AP exam. It is not on the IBSL exam. It actually is taught on the IBHL exam, but we're not taking that exam. So, this is showing you what the Iranian Equation is. It relates the constant. I like this format right here. I'm going to highlight. This is the y equals mx plus b format, and we talked about this briefly in class. where you can graph the natural log of K versus 1 over the temperature in Kelvin, and you will get a straight line where the slope of the line is negative EA over R. And so this allows you, if you know the rate constant at different temperatures, any two temperatures, you can find the activation energy. Now there's a special sort of point here where the y-intercept is, and that is ln of A, and that is called the frequency factor, and that's a constant that relates to the equation. Now, this is important if you want to actually solve for activation energy, but there's another form of this equation which I really like, and that form of the equation's at the bottom of the slide here, and that actually allows you to find activation energy, and this one gets rid of A. And that's nice because A is sort of this elusive, constant that you would need to find. That would make it more complicated. But now we can get rid of A and we can solve for activation energy in the equation here. And so this just shows you what the form of the equation looks like, and gives you an idea of what they are of what they're doing. So the last thing I want to talk to you about is catalysts and enzymes. And so when we do catalysts and enzymes, we know from last year that in fact the catalyst will lower the activation energy. That the catalyst will lower the activation energy. And I like this because this graph shows you how a catalyst could also work by providing an alternate pathway. You've heard that as well. So if we write this, catalyst lowers the activation energy, but also it provides an alternate pathway. And now we know what a mechanism is because we spent some time doing that, and the mechanism changes. So instead of just having this one overall reaction that they show in red here, uncatalyzed, now they have a catalyzed that actually takes place in 2 steps. And what's cool about it is they have an arrow pointing here, and they show this, part here, and this is called the intermediate. So here's where my intermediate is. Remember, an intermediate is where you have this product that's formed that then gets used up in the reaction when you go to the products, and in this case it would be the water there that would get used up, and the bromine. Actually, sorry, the bromine would be the intermediate. The water, it's produced in the end here. I didn't see that. So this reaction is showing the difference between a catalyzed, uncatalyzed reaction. Now, when you look at a catalyst and you think about, what's going on with this here, one last thing I want to mention is a catalyst will show up in the beginning and the end of a reaction in a mechanism. Sometimes they'll ask you to identify, is it a catalyst or not? So if I had A plus, X, and then, it forms B, this is step 1, let's say. And then in step 2, I have, B plus C goes to D plus X. If I wrote the overall reaction, I would get A plus C goes to D. So I have 2 components here, B, that don't end up in the final, and X, that don't end up in the final. B is an intermediate because it's generated in the first reaction, and then it's used up in a subsequent reaction. X is a catalyst because it starts in the beginning, it's added in the reaction, but then it's regenerated at the end of the reaction. That's what a catalyst does. When they say a catalyst is not used in a reaction, it means that it's reacted and then regenerated. So that is kinetics for you. I hope that you enjoyed these lectures, and we will definitely go over this in class tomorrow and finish up the chapter. All right, thanks so much for watching.